Okay, but I'm not really going to continue. I'm going to kind of start again from 0. So you may now forget everything I said before, which was, and we're going to do something similar, but it will now be in the group situation. So instead of that Lie algebra with 3 relations, I'll be talking about the group GT with 3 relations. And instead of all the multi-zeta values and the real numbers in the number theory, we'll be talking about Galois Q bar over Q. So it's a kind of higher up analog, starting again. So I'm going to talk about Grothendieck-Teichmüller theory. What is it? What's the theory? What does it say? What does it do? What did Grothendieck invent it for? So the point is this. The point was when Grothendieck invented this, so from now on in my next few lectures I'm going to be talking in these terms, the point is to understand something about this group. The linear thing that I was talking about before and the fact that you can also understand maybe something about multi-zetas and so on, this is something that appeared later in the theory. But the origin of the theory, the way Grothendieck invented this theory, the purpose was to study this. The thing is that we don't understand this group. This group is incredibly not understood. We know that it is profinite. So it's an inverse limit of, well, of its finite quotients, but we don't know who they are. So finite groups G, but we don't know which ones. So certain finite groups G, those exactly which occur as finite quotients. Of course, one conjectures they all occur, but we don't know. We just don't know what finite quotients occur. We don't know anything about this group. It's terrible. Let me tell you the one thing we do know. We know that it breaks into 2 pieces naturally. We have Gal Q bar over Q ab, where Q ab is the maximal abelian extension of Q, which is just Q adjoin all roots of unity. So it's a maximal abelian extension. And in the middle we have, I'm going to call this group GQ from now on. And here we have Gal Q ab over Q. So this helps somewhat in that it breaks it into 2 pieces, at least one of which is well understood. This, it's just the roots of unity. This is an easy group to understand. I'm going to tell you what it is. It is Z hat star, which is the inverse limit of Z mod NZ stars for all n. Now, inverse limits is one thing you really have to brush up on if you're not familiar with them, because they keep coming up all the time. I don't have time to give you the definition, but once you have it, it's not hard. This we don't understand. This is the hard part. This is the really key hard thing. But we do at least have a conjecture. So the conjecture, which is Shafarevich's conjecture, this group here would be free. Free, profinite, unaccountable number of generators. But I mean, no progress has been made on that conjecture. But it's sometimes useful when we study this group to break it up into 2 parts and just kind of concentrate on the hard part and get rid of that. Okay, so what have I told you so far? I've told you we want to study this group. We don't understand it. We don't understand its finite quotients. We don't understand it by generators and relations. We just don't have a handle on it. We know what it is. We know that it's automorphisms of the algebraic integers, but that doesn't seem to help that much. So what Grothendieck said is this. He said, you should study this group geometrically. You should study its action not on algebraic numbers, which we have studied and it just doesn't give enough, but on geometric objects. And by geometric objects, he essentially means fundamental groups. The point is that this group acts on fundamental groups. In fact, we saw this at length in Makoto's talk this morning. If you have X is a variety, an algebraic variety defined over Q, then, well, there exists an exact sequence. Well, let me see. If Q of X denotes the function field of X considered as a variety over Q bar. So here, Q is defined over, X is defined over Q, so we have a function field of functions defined over Q. But we can just as well consider X defined over Q bar if we want. and get a function field here. And as Makoto told us this morning, here the Galois group is none other than just GQ. Now, this is in function field terms, so that we can have a Galois group. Correspondingly, here's the variety x over q, and here's the variety x considered to be over q bar. And here, up here, we're in topology now. Once we're over an algebraically closed field, it's just like being over C. We can have a universal cover up here. Universal cover. And here, the Galois group is the topological pi 1. Now, let me not really put there's no morphism here, so let me take that line away. But you consider this as on top of that, in a sense. You get this from that by tensoring, by augmenting the scalars. Now, this is not an algebraic variety, so I can't just take its function field, but I can do something pretty close, and this is what one does. I will look at everything between the two, so all covers of x which are just finite. So the Galois group here would be a finite quotient of pi 1. These are finite covers of x, so they are algebraic varieties. So they have function fields that I can put as finite extensions of this. And what I do is I take the compositum of them all. I'm writing union here, but what I mean is the compositum of all these fields. That gives me a big field upstairs. So let me call that big field q of x with a big twiddle over it. Now what is the Galois group here? It's not exactly pi 1. Because here, this is not, you can't really consider this as a function field of that, because this is not an algebraic variety. But it's very close to pi 1. In fact, what it is it's a whole system made up of each piece, which is all the finite quotients of pi 1. So what it is I'm going to call it pi 1 hat. It's in fact just, so it's this big qx twiddle. Oh, I should even add a bar so that you remember that it's q bar is the constant in there. It's just the profinite completion of pi 1. The profinite completion of something means I take the inverse limit of all its finite quotients. So n is normal in pi 1, and pi 1 over n is finite. And you can really see that when you look at this. I haven't taken the big thing right away. I've taken all of the finite ones here, and I've put them together in a coherent sequence. So the Galois group here is that, pi 1 hat. And the Galois group here is GQ. So what this is giving me is an exact sequence. 1, pi 1 hat, gal of the great big thing over the bottom field, GQ 1. Now, this is to be thought of as exactly what Makoto was doing this morning. It's the same exact sequence. And when you have an exact sequence like that, always to say you have an exact sequence like this is the same as saying the kernel acts on the quotient. You have a canonical homomorphism from the kernel, from the quotient into the outer automorphisms of the kernel. A sequence like this gives me a map like that always. That's how you construct this middle group. And this is canonical. Once I've fixed my variety x defined over q, I get this for free. So why did I tell you this? I told you this because I wanted to justify the fact that GQ acts on fundamental groups. This is what I mean by a geometric Galois action. It's Galois acting on a geometric object. Galois is now acting on the fundamental group of a variety. It's geometry, algebraic geometry. So what Grothendieck suggested is, suggestion, I don't like that word, vision, let's say it's vision, sounds bigger, but we look at these groups, I mean, for specific varieties, specific, good, simple varieties that we know, like above all, our friend, P1 minus 3 points. We know everything about them. They're free, or we know their generators and relations. I mean, we know them. So if we can write down for the elements of GQ how they act specifically as automorphisms, we can get maybe some information on it, like on its elements, on their relations. We can get a completely different view. So get information on GQ by using the structure, the group structure of the pi ones. So I want to do this in 3 steps. Only one today and the other 2 in the other 2 talks. The first thing he said is, well, if pi 1's abelian, nothing's going to happen. Because if pi 1 is abelian, the whole GQ action is going to factor through this. And this we really understand. We won't learn anything new. We know this very well. We know this. Let me remind you what this group is, actually. An element of this group, sigma of a root of unity, an nth root of unity. Well, what can it be? It's an Galois group of Q of roots of unity. It has to take it to another nth root of unity. So, in fact, if this one's primitive, it has to take it to a power of itself. And that power is called chi of sigma, where chi is just the map, GQ to this quotient here. That map's called chi. You get a number which is in here. This is weird, because it's a complicated profinite number. But when it's acting on something which is of order n anyway, it just becomes something mod n. So chi of sigma.
I don't understand. When you say pi 1 is abelian, the action factor is from power to abelian?
Yes.
In general, that's really not true. You don't take an abelian, right?
Oh, no. Well,
Yeah, it's true in that case, but certainly not.
okay. Yes. Fine, fine. Okay, let me say something. Let me say, I didn't say that. And let me say, let me just not. I don't want to get into it. The case where pi 1 is abelian is maybe interesting in certain cases. But in the case that the Grothendieck wanted to look at, that case does become trivial. It's the case of the moduli spaces. So I'm going to restrict to very few pi 1s later on and study them. And in that situation, the abelian ones will not be interesting. Okay. But in general, okay, the first thing to look at is this. The pi 1 is not abelian. If you look at p1 minus 2 points or p1 minus 1 point, the pi 1 is abelian, and what I said is true. It factors through the cyclotomic character. So it's not interesting. This is the first interesting case for a lot of reasons. First of all, it's a one-dimensional variety. It's in low dimension. Second of all, its pi 1 is really simple because it's free on 2 generators. Everything can be calculated about the action here. So it gives us a first really important piece of information.
I don't want to sound too contentious, but it's kind of, I think it's misleading to say cyclotomic character is uninteresting.
Okay. Cyclotomic character is well understood. Will that do? Cyclotomic, it's a terrible habit of mathematicians to say that what's well known is not interesting. It's true. I will buy that. Cyclotomic character is well understood. Okay, now here's something interesting. After having looked at this case at length, and this is what I'm going to look at today, Grothendieck, he used some work of other people, and he wasn't the only person looking at this situation. And several people tried to generalize this idea, and the natural way they tried to generalize it was P1 minus more points. And then things get really difficult because this whole situation starts depending very much on which points you take and not just how many points you take. Whereas what Grothendieck said was, no, you should not generalize this by taking P1 minus more points. What you want to do is look at moduli spaces of curves, and this is the first moduli space of curves. And then you should look at general moduli spaces, and that's the right general situation to look at. He said, to look at all fundamental groups of all curves is much too complicated because for an arbitrary, no, I didn't even mean curves, all varieties. For an arbitrary variety, we take the pi 1, we don't know how to calculate this action. And what he said is, for moduli spaces, you should be able to do it. He gave a few very abstruse hints about how to do it that turned out to be absolutely and completely true, and everything he said turned out to be right. So, because of work by Drinfeld, which greatly facilitated understanding of his program, I'm going to He didn't say look at genus zero moduli spaces. From this he passed to the general case, but it's very nice to have this intermediate step. I'm going to be explaining what moduli spaces are. But this intermediate step is nice because the genus zero ones are much easier to understand. And already you get something interesting from this level, okay? So basically this talk, next talk, last talk, it's going to go pretty much in this order. And what I'm going to be aiming to tell you is what we can understand about GQ by looking at this situation. So some things that we can find out about GQ. Okay, so one thing we know about the action of GQ on a fundamental group, and we're going to be using it all the time, fact. The GQ action on a fundamental group. When I say fundamental group, I'm always going to be meaning algebraic fundamental group, that is the profinite completion. And I'm always going to be meaning of a variety defined over Q. Sometimes I may cheat a little bit. It won't really be a variety. Okay, it might be a quasi-variety or a stack, but it will be the same situation, basically. Preserves inertia. So some fundamental groups have inertia subgroups. Inertia subgroups, I'm just going to remind you to go back and look at the definitions in your books. I'm not going to give you the definition now. But you remember, here we have an extension of fields, and you just have to remember the definition of your prime ideals, well, the ring of integers, the prime ideals, the inertia subgroups. Some pi1s have inertia subgroups, sometimes there aren't any. It depends on the ramification that you have. But whenever you have inertia subgroups, are cyclic. Say we have a subgroup like this inside our pi1. And let me just tell you what I mean by the action preserves inertia. What I mean is sigma of alpha, if alpha is the generator of an inertia subgroup, it's always going to be of the form gamma minus 1 alpha to some power gamma. Okay, so up to conjugacy, and I could also write this as sigma of the group alpha gamma. So let me write up to conjugacy. This is something very special, and it's a very fundamental property of the Gauss action. And it already gives some information in terms of groups. So we're going to look at our basic example. P1 minus 3 points. So although, of course, the fundamental group of this is free on 2 generators, we're going to write it with 3 generators so that we don't treat these 3 missing points differently. We're going to take a tangential base point, just like what Makoto was explaining to us this morning, right here. So just consider it to be a little region near 0. I'm going to take a loop around 0, a loop around 1, and a loop around infinity. And we're going to call those x, y, z. And when you take the product of them, that's equal to 1. Now, each of these 3 loops generates an inertia subgroup. The inertia in pi1 of x, let this be x, based at, it doesn't matter where I base it. For convenience, I'm going to base it here, but of course what I'm going to say is always true, whatever the base point is. So it's the cyclic group generated by x, the cyclic group generated by y, the cyclic group generated by z. So let's see what that tells us about the Gauss action on it. Let's see just this fact alone. Well, we have GQ maps to the outer automorphisms of our F2. I'm writing pi1 of x or F2 indifferently. F2 is to be thought of as being generated by xyz with xyz equals 1. And let me take sigma. Now, I'm going to lift sigma to an automorphism. It's only defined up to inners, because it's really canonically defined as an outer. So when I lift it, it's defined up to inners. So I can pick one lifting, a lifting of sigma to an automorphism, such that sigma of x equals x to some power. Because, I mean, in principle, I know it's conjugated by something, so I can just apply an inner to remove that conjugation. Now, y is also an inertia element, so I know that y, let me use an f here. Let me use an f twiddle. By the inertia property, I know that it's going to act on y like this. Okay, and z also. There will be some g. Okay, now, I'm coming up to the very, very nice thing that I want to say first. This is very striking. I'm going to look at the abelianization of my F2. My group is a free group on two generators, so when I abelianize it, it's just Z cross Z, generated by X, Y, and Z, but they now commute. And therefore, in fact, since this is an automorphism of the group, it has to go down to an automorphism of the abelianization. The conjugation goes away in the abelianization. I've just sent x to a power, y to a power, and z to a power in the abelianization. And that has to form an automorphism. But the only relation is this one. So by abelianizing, we see that alpha equals beta equals gamma. Because x to the alpha, y to the beta, z to the gamma is not going to give you an automorphism of the abelianization otherwise. So, sigma of x equals x to the alpha, sigma of y equals f something, y to the alpha, f something. Now, I can always change this by an inner. Remember, it was just a lifting. I can always change it by an inner by a power of x without changing the first line here. So I'm going to do that. Modifying my lift by in of some power of x. What that does is I substitute. It's like changing f into f times some power of x. And of course I can modify f on the left by a power of y, because that won't make any difference to sigma. i.e. modifying the choice of f twiddle by doing that to it, which I can do without changing my lift of sigma at all, or just by an in, which I'm allowed to do. What I can do is I can get a unique f twiddle with a nice property. Gives another lift of sigma. But among all possible choices of this, for all powers mn of x, there exists a unique choice, f, in this set, which has this property, which is in f2 prime, which is the kernel of well, it's the derived subgroup of f2. But because this is profinite, you have to be careful when you say what that means. It's in a topological sense. So another way of saying it, I just want to give another equivalent way of saying it, is f is in the kernel of the map f2 maps to z hat by x maps to 1, and it's in the kernel of the same map, but here I let y map to 1. So I have two maps here which send my group to a cyclic group, but f has to be in the kernel of both. Now it's pretty obvious that since I give it any f twiddle, I can put a unique power of y on one side and x on the other to make this happen. I just take away the power that I would get out of this, okay? So now I've chosen an f, which just gives me another lift of the same sigma, but which has this unique property, it's an f2 hat prime. So what I've done is I've associated to sigma. So to every sigma in GQ, I have associated a pair alpha f alpha is that power, and F is in F2 hat prime. So, as it happened, this power, it's easy to see that this power is nothing but chi of sigma. So this power is what I would call, I dare not say this now, but the not so interesting part of the action. Alpha is just this. Now you're so far back I can't hear you.
The kernel of the map from F to hat is U hat.
Yeah.
Sending X to 1 and Y goes to where?
1. Oh, no, X goes to, oh, sorry, good heavens. 0. 0. If you think of this additively, I was thinking multiplicatively in my head, that's why I said, no, X goes to 0 and Y goes to 1. Yes, and Y goes to 1. And X goes to 1, yeah. One goes to the generator and the other goes away, is what I mean. It's just, if you think about it, it works fine in the discrete. The same thing works fine for the discrete definition of the commutator subgroup. It's words whose total power in Y is 0 and total power in X is 0. Just another way of thinking of the commutator subgroup. So, what I have here is a map. Okay, I have a map. Now, this is very interesting because here's something which is really, really hard to understand, and here's something which is really not that hard to understand. I mean, the image is hard to understand. But F2, what is it? It's F2, right? It's the free group onto generator. It's really a lot easier to look at these elements, especially if you take what I said, the interesting subgroup Gawa Q bar over Q ab. The cycloatomic character is 1. This part's trivial, and basically what you're doing is you're mapping gal Q bar over Q ab into F2 hat prime. Now be careful, it's not a group homomorphism. It's not a group homomorphism. Not with the obvious group structure on this, the obvious multiplicative group structure. It's a group homomorphism, but for that you need to put a different group law. On C hat star across F2 hat. But I'll show you how to put a very simple, it's really not that bad, different group law on this that will make it into a group homomorphism. So, new group law. It's really obvious when I say it, it just comes from what we're doing. Take a pair lambda F and let it give an endomorphism of F2 hat. Okay? Just by, F2 is a free group, so I can send X and Y anywhere. I'll always get an endomorphism. So I just send X to this, I send Y to that. Gives me an endomorphism. And the new multiplication law will be composition of endomorphisms. New group law is just compose endomorphisms. If I call this endomorphism F, then the group law is given by lambda F times mu G will be lambda mu F of G, I think. You can test it out for yourself, but it's pretty simple when you actually just compose, you put one endomorphism and then you apply another. So this is what Grothendieck basically indicated. Roughly, not without any formulas, but essentially, he described this. He said there's a map like this. He said, look, an element of GQ you can just look at as an element in the free group on two generators. So please, somebody, find the image. Find out which elements of here come from there, because then we'll have a wonderful description of GQ. So this, in a sense, was his goal. And the way he suggested doing it was to look at the action on all the fundamental groups of moduli spaces. But before doing that, he got sidetracked, and so I'm going to get sidetracked the same way as him, because I want to tell you about dessin d'enfant. So look at what I'm going to say. Next talk, we'll start directly from this point and go on. What I'm going to do now is an interlude, just telling you what I can tell you about P1 minus 3 points. I'd like to get more deeply into the fact that there's a Galois action on this fundamental group. look at it differently and see what the combinatorics of it looks like. So this is disanofo. Another way, a combinatorial way of looking at the Galois action on F2 hat let me give us a base point. So what is a dessin enfant? A dessin enfant definition is a collection of, finite collection, vertices and edges. I'm going to write finite. On a topological surface, which can be of any genus, so let me say of genus G, any G, which just has a couple of simple combinatorial properties. So for one thing, it's connected. And for another thing, if you cut along the edges, when I say the dessin cuts the surface, I mean if you cut along the edges into cells. Cells are like just open regions, not tubes or cylinders or anything more complicated. And 3, you can color the vertices in 2 colors, so say black and white or something, in such a way that all neighbors of a vertex have the opposite color. This is just a technical thing. Neighbors, of course, mean that I have edges leading to other vertices. And a neighbor is just, if I have an edge coming out of my vertex, it's the vertex on the other end of that edge. So I'm not allowed to have any loops like this in my graph. If I have such a loop, it's got to have another vertex in the middle of it. Otherwise, I don't have a dessin. So what you've got, if your genus is 0, and so your distils are on the plane, you've got, this is really why he called them distils. Because what he said was they're so incredibly concrete, I mean, that any child's drawing is just a perfect example. Well, people frequently favor this one also. But of course, you can also have them on torus. Just put in some edges. Go on and on, do as many as you like. Okay? Now, the whole point of these distils is that they are in bijection. They're a very, very simple combinatorial object, but they're in bijection with something really important. I'm not going to the details of, obviously distils are defined up to isotopy, and it's basically just the topological shape which counts. With conjugacy classes of finite index subgroups of F2 hat, or without the hat, because it's the same thing when I'm talking finite index. Doesn't matter whether I put the hat or don't, which are in bijection with, here I'm going to basic Galois theory of varieties, which I think Makoto will be talking about more in his talk, with finite covers of, what is this? It's just the pi1 of p1 minus 3 points. So its finite subgroups are in bijection with finite covers of p1 minus 3 points. Oh yeah, finite index, yeah, right, finite index. Certainly, there are not very many finite subgroups in a free group.
Sorry,
You mean these dessins? No, these are 3 different dessins.
No, but are they but they're all dessins?
They're just examples of dessins.
You need some more vertices.
What?
You need some more vertices.
No, these are dessins. These 3 are dessins.
The guy's head.
Yes, well, he has a little thing there. He's got a little thing there. Yeah, well, I haven't colored the vertices for you. You do it, whatever. Put them wherever you need them. Whatever. I think it works now. Yeah, I omitted to draw the vertices, but you can always draw them. Anything in genus 0, the thing about cells isn't even a condition in genus 0, because when you put it on the plane, it always has to cut it into cells. Huh? Okay, so, well, the subgroups? Finite index subgroups are open, but anyway, you can even do this in the discrete, it doesn't make any difference. Finite index subgroups are our basis of the topology, so the open ones. But in this, it doesn't matter, because here you're looking topologically. Yeah, all finite index subgroups are open. It's true for this group. Can I just erase the hat? Okay. Of course, if I erase the hat, everything remains true, but now I don't have a Galois action anymore. However, since we know that there's the open finite index subgroups of F2 hat under conjugacy, meaning conjugacy classes of, are in bijection with the covers that I just wrote here. But we saw that Galois acts on this. Okay, so Galois, of course, acts on the subgroup, which sends it to some other subgroup. So what that means is it acts on a cover, sends it to some other cover. But GQ acts on the former. We just saw that. That was the whole point of our GQ acts on F2 hat thing. So it acts on dessins. Right? These are in bijection with dessins. Now that's where things get really surprising. This is the kind of thing that really charmed Grothendieck in his later period, I should say. Is here's Galois acting on this now, and where on earth does it take it? What does it do? So, goal of dessin d'enfant theory: combinatorially determine the Galois orbit of a dessin. So what combinatorially determine means is, ideally, is give invariance. Give a bunch of combinatorial invariants of a dessin which pick out the Galois orbit. When I say combinatorial, I'm really using the word in a large sense. Anything algebraic is great. As long as you're not saying, take the dessin and do a huge operation which will actually give you back the whole cover with its algebraic equations and everything, and then once you have that, you take GQ on the coefficients. Okay, you can do that, but that is really not what I call combinatorial. Let's say combinatorial invariants ideally would be things like integers or groups of dessins which are, which describe the Galois orbit. So one thing is pretty obvious is that when the Galois group acts on a cover, the thing is, if you're given a dessin, you can find the cover topologically. This is like giving a topological description of the cover. And you know by this, you know that it's then an algebraic variety, and therefore there are equations describing it. And if you had those equations, they're defined over Q bar, because it's a finite cover of something defined over Q bar. And so you could just apply GQ to the coefficients and get the new cover. But you can't really do that. It's not feasible. Once you have the descent, to get the whole equation, you can do it on a computer in some very small cases, but you can't really do it. So that's not what's wanted. What's wanted is a description in the language of the distance, that isn't something really combinatorial. So, however, at least you can say a few things. If you can say that anytime Galois acts on a cover, it preserves the ramification. These are covers which, well, they're unramified over P1 minus 3 points. But this is, this is Riemann surface theorem. You can complete them to a cover of P1 ramified only over 0, 1, and infinity. And in fact, what is the descent? Now I can tell you exactly what it is. If you, under those bijections there, your descent belongs to a cover like this, and it's just here you have the segment 0 to 1, and up here you've got its pre-image. The pre-image of that segment. And that's exactly what the descent is. It's just the pre-image of that segment upstairs. So this is a topological surface with some G as G, and on top of it sits a bunch of segments, all the pre-images of that. And here you've got ramification. Over the endpoints you've got ramification. So what that means is that at every point, which isn't 0, 1, infinity, you have the same number of points on top of a given point. But on top of 0, 1, infinity, you might have less because of ramification. So that's why you have a graph. And in fact, the ramification are, the black vertices are like the pre-image of 0, and the white vertices are like the pre-image of 1. Or vice versa, depends on the convention you use. Okay? So the interesting thing is, any cover like this is obviously going to give you a descent, and any descent will give you a cover.
Actually, the thing that you said we can't really do, at least in theory, is that something you can effectively determine from the descent of the curve?
What kind of thing? You're talking about equations or what? I mean,
And is that the computational power of the
there's a lot of things I can tell you that we can't determine. For instance, it would be wonderful if we could determine even just the number field of definition, or even the degree of that number field. But even these things, we can't just determine them directly from the descent. What you have to do is, literally you can't do it. I mean, really you can't do it. You can write down a huge number of equations and try to solve everything to have all the right ramification information and so on, and then you get a finite number of descent with the same ramification thing, and then you can try to figure out which one was your descent. But it's really not feasible at all, except in the smallest cases. The trouble is the only thing that we can say now is really very simple compared to the full problem. So one thing you can say is that the Galois action on any cover preserves the ramification indices. It's not going to change that. So sigma of a descent, what we do is we associate to a descent, for instance, its valency lists, which means valencies. Valencies are the number of vertices coming, the number of edges coming out of a vertex. So the black valency list for this descent, for instance, it would be 3, 1, 1, 3. Not in any order, it's an unordered thing. And for the white valency list would be 1, 1, 4, 1, 2. The infinity valency list, you can do it if you want. The infinity is the cells. So there's one cell here with a valency 2, and another which has 3, 4, 5, 6, 7, 8, 6, I guess. This is a degree 8 descent. Okay, so I'll get a new descent which has to have the same valency lists. Because really ramification indices are preserved when you act on a cover. That's something you can easily see by, if you know that the cover is given by equations. So even if you don't know what the equations are, you can immediately see that the ramification has to be preserved. So, but what that means is that the candidates to be the Galois orbit of this descent, there's only a finite number of them. Because if I give you the valency list, there's only a finite number of descents with them. So the set of descents which might be in the Galois orbit is finite since they must have the same valency lists. So they have the same number of edges in particular, same number of vertices, same number of valencies. But now we get to the nitty-gritty, which is, well, and so which ones are in the Galois orbit, which ones aren't? So let me just give you a few of the invariants that have been found up to now. There have been various people who worked on this and have found various invariants which have, we say separating distance. What we mean by separating distance is we take two that have the same valency list and we determine that they are or they're not in the same Galois orbit according to such and such an invariant. So further invariants. So what is the Galois group of the dessin? So what is the Galois group of the dessin? Well, it's just the Galois group of the Galois closure of the cover x over P1 minus 3 points. Okay, now this thing may not be a Galois cover, right? Up here you have the usual, and here you have the pi 1, and this subgroup might not be a normal subgroup, so you take the normal subgroup, the intersection of all the conjugates of it, and take that normal subgroup. That's the Galois closure, just like standard Galois theory. Well, two distants in the same Galois orbit have to have the same Galois group. Then there's another one. Okay, this is interesting. Whenever you compose here, you can take a dessin and you can compose it with a function, with another function. Let's just write P1, P1. Remembering always that the dessin in the end has to be ramified over the 3 points only. You can compose it with another function from P1 to P1. And what you get is a new dessin. And by building up these sequences of dessins, which deep down are the same dessin, but yet they're different, you can build up dessins by composing, creates new Galois invariants. Well, you change the degree, so no. Actually, no, I'm not getting into the detail of it. You can build up invariants in this way. But you don't, not as easily as the way you just said, because when you do this, you change the degree. But by doing this with two different dessins and building down, sometimes you can determine whether they are or are not in the same orbit. You start with two that you don't know, and you do this thing. Okay, here's something which, again, I'm not going to tell you the details, but it's, yeah, I won't tell you the proof, but I'll tell you the result because it's really pretty. If you look at dessins which are like what we call diameter 4 trees, so you've got some things around a central vertex, and then you've just got some tails there. So the valency lists are N1, lots of ones, and then it's some A1, AN. Here, very often all possible permutations of the central branches are in the same Galois orbit, but sometimes they're not. And sometimes it breaks into pieces. And by doing a lot of computations, there was a Russian mathematician he did a lot of computations on these. For instance, here's an example. When you take 1, 2, 3, 4, and 5 tails, and you then take the same tree, but where you just switch 2 of the branches. So I just switched 2 of them. These are not in the same Galois orbit, strangely, whereas usually when you do this, they are. But sometimes it happens that they're not. And this mathematician, he did just lots and lots of examples to figure out when they were and when they weren't. He came up with this cute formula. When this number is a square, a1 plus an times a1 times everything up to an is a square, then the distance which are diameter 4 trees, break up into 2 Gawa orbits. So a priori, how many of these descents are there? They are just going to be all permutations of the central branches, but up to rotation because that's just an isotopy. So n minus 1 factorial. So generally, all n minus 1 factorial form 1 Gawa orbit, but in this case, they form 2 Gawa orbits. One is the an permutations, and the other is the rest. And the others. So let me just say even permutations and odd permutations. And odd perms of the branches. So each of those forms a Gawa orbit, okay? So this is very, very cute. So this was proved later by a student of mine called Zapponi. This was his thesis work, and it was a very, very nice proof because he really found the two of them together, their joint work, this is the kind of thing exactly that I mean by a Gawa invariant. It's the simplest thing in the world. It's a combinatorial little thing. It's an integer. And it just tells you these are or are not in the same Gawa orbit. So it would be wonderful to have, so this family is essentially solved. It would be great to have stuff like this that would do the general case. So this should really be seen as an interlude, like a picture of what kind of thing you can do.